So, welcome everyone to our next talk. Dr. Heinrich Hartmann will tell us about the friends and foes, and I hope the technical ones, in monitoring APIs. Give him a welcome applause.
Thank you very much. You always note that you're at a German conference when they say the doctor in front of your name as well. But it's a great opportunity to be here. Thank you very much to the organizers, and thanks for showing up to the talk. I'm going to talk about monitoring APIs. Before I do, I just wanted to give you a brief introduction about myself. Like, this is how I look. You might have guessed by me being here. My background is I'm a mathematician. I did a PhD in pure mathematics a while back in Bonn. I'm originally from Mainz, so from the Rhine Valley. I've spent most of my life near the Rhine. After like a pretty extended journey in academia, I finally switched to IT and to system administration and IT infrastructure. It was like a interesting journey. You can ask me over at a beer tonight how that precisely went, but right now I'm the analytics lead for a monitoring company called Seconus. Who of you has heard of Seconus? 4, perfect. So more than I expected. This is a perfect excuse to just say 2 or 3 more words about Seconus, because it's actually a pretty nice product and pretty nice platform that is a little bit not so well known. So yeah, right, we are an analytics vendor or a monitoring vendor. We have a SaaS product and actually an on-premise product which you can use to monitor your infrastructure. We are actually pretty old. So we are from 2010. We were one of the first companies who did monitoring as a SaaS product. Back then, when the infrastructure landscape looked very different from it is now, we were basically competing with Nagios back then. And right now, we're still competing with Nagios, but also with other people. We are a spin-off from a consulting company called OmniTI, also Washington, DC based, which specialized in Postgres monitoring. And Seconus was a spin-off because our founder just couldn't stand the pain anymore of using these tools back then to monitor their infrastructure. So he decided he has to build something else. And so the culture within our company is very engineering focused and engineering heavy. So we basically build most of our infrastructure completely on our own. First thing is we run our own operating system. It's called OmniOS, which is a product of the company OmniTI, which we are a spin-off of. It's a Solaris-based operating system, which has like ZFS and zones as core features of Solaris. Some of you will know. Zones is the stuff which is now called Docker and containers. It's been in Solaris for 10 years plus, 15 years maybe. So all that, we've been using this for a while. We have our own in-house database. It's basically a Timeseries database, which is Cassandra-like, highly scalable. We have our own queuing system. We have like built a ton of things on our own. We're very engineering-focused company, and we are actually using our own tools, of course, to monitor our own infrastructure as well. So this is a little bit in contrast, and I have had this discussion with Avishai, who's here today as well. It's very much in contrast with what people nowadays do. Like, we see a lot of people who go to the cloud and have a very thin application stack on their own and try to outsource everything else. We do the opposite thing. We just have everything built out ourselves, which has advantages and disadvantages, but it's also, monitoring is a very different type of stuff you do than operating a web store or something like that. It's very different type of read load and write load that you're serving. So it might be interesting trade-off. Actually, it works quite well for us. So one thing that we can do well is we are extremely cost efficient our infrastructure. So we have clients which push like we had one which was doing like around the scale of 50 million metrics, and they were using 60 nodes for doing their monitoring. So we cut that down to 7 nodes with our own database. So like the scaling effects are there, and it's dependent because we control everything on the full stack. So advanced analytics, I will talk about this a little bit more and show you a few things that we can do with different parts. It has forecasting method, it has anomaly detection, outlier detection, and a query language that we call capable. And below here, I put some of our customers. Right. So, right, so I misused, or actually shamelessly used this time I had here to talk about our offerings that we have as a product. But actually it's an open source conference, so I just wanted to say we actually consume open source and we contribute open source as well. I mean, first of all, OmniOS is a open source operating system that you can also download yourself. And we have a few tools available in the monitoring landscape, which are interesting. They don't have a terribly high uptake, but they are used like by us extensively and some other people as well. So first of all is NAD. It's a node-based lightweight monitoring agent, which is actually pretty neat. So first of all, the extensibility aspects of it are pretty nice. And here's a thing that we'll just briefly talk about. There is a ongoing debate about push versus pull in monitoring. So you can either expose an HTTP port and just pull the metrics out, or you can point your agents at a centralized host and say, please get the metrics in. Both have advantages and disadvantages. One thing that is often confused is here that you are actually doing two things. You are opening a connection and you are requesting data over that connection. And you can switch the direction of those two. You can decide which side initiates the connection and which side initiates the or pulls the data. And we use with this agent a method we call reverse pull, where the agent opens the connection and the server then requests the data. This has very nice implications. So it doesn't matter if you're behind a NUT, your attack surface is lower because you don't expose a port, the agent opens the connection. But the monitoring system has the ability to control the data collection cadence. So, for example, if you do real-time dashboards, you might want to have 1 second cadence. So if you're debugging something, you want to know every second what's going on. And this stuff you can do nicely with the reverse pull. Okay. Then there's Reconnoiter, which is our what we call broker. Also a very interesting piece of technologies which allows to aggregate metrics and stream them forward and also run checks on its own. This is a FQ, that's a message queue. libmtap, it's a C level application framework we use heavily inside our own infrastructure. It's a little bit bad documented, but it's also like really a powerhouse. And then there's libcirclehist. It's a histogram tool, and I will talk a little bit about that later. This is also available open source. And actually, today is a very important day for us as a company as well. And right here, right now, is the time where we will announce a big release of a new product, which is called IronDB. It actually fits this purpose very well. I didn't really know that would be speaking here today to actually make that announcement, because it's a time series backend for graphite. So if you run graphite, and you know you can do Whisper files, you can do Carbon, you can do InfluxDB, now you have a way to actually ingest graphite data into our own proprietary time series database. And this is a distributed time series database, which is like highly scalable, can do millions of metrics, and is like you can install that on premise. It's not a SaaS product. Just to download it, you need to run OmniOS. So at the moment, you have OmniOS packages for this. We will have an AMI for that soon, so you can just spin up an Amazon node and just say here, point the metrics to it. But it's distributed on the node, so you can run as many nodes as you want. The pricing is the first 25 metrics you get, 25,000 metrics you get for free, and then we have pricing steps of 100,000 metrics and 100 million metrics. This is so the first 25,000 metrics you get for free. You can use as many nodes for this as you want. You can use it on a single node, but you can also have 5 nodes or something like that. So you get the distribution aspect for this for free. And if you are really buying a large account, we will be at a price of 1 cent per metric per year. This is yearly pricing. So it's actually pretty cheap if you are going that scale. Right. So I won't take too much time to talk more about this. Come approach me. We have a little bit of marketing material down there at the road. So if you want to pick up a T-shirt like that or stickers, we have it over there. And come to me if you want to know more about it. Okay, so API monitoring. This talk is actually comes from a history of talks and topics we have been discussing in the last year. I've been talking about statistics for engineers a lot. I've written about much of this actually in the ACMQ and the CACM, Communications of the ACM. There are 2 articles there, also called Statistics for Engineers. And it's basically the story about how to apply statistics in the monitoring domain. And it's how to do that well. And it's particularly relevant for APIs. So I will have the slides online soon, and you can have a look at the references there as well. But this is not coming from the vacuum. This is actually a long-time effort we have to talk about how to do statistics properly and how to read the data that is emitted and stored in your monitoring system. So, to make this a little bit more plastic, I have chosen to use an example use case we can all relate to. So this is a completely fictional web fashion store called Zalando, which serves fashion products, and it has a catalog which it serves over a web API. And they have this funny property that they lose money if the requests take too long. I mean, many people will be able to relate to this. If the site is slow, then it's a problem. And this is just an example. I mean, APIs are basically everywhere and they're getting more and more important, but right now this is the easiest example. You just serve web requests. What do you want to do with the monitoring? I think the first and the most important thing is that you want to measure the user experience that you have. You don't really care if the data center is burning, to use this famous metaphor, as long as the user is being served. So you want to really understand how your users are behaving. You want to assess quality of service if you have the formalized SLAs or something like that to measure the user experience. You won't always be able to serve perfect quality service. So you might want to know where's the problem and help to locate this. This is actually not on the slide, but that's a very important property of that. And you want to be able to negotiate some level of service degradation. You want to allow and have some budgets with the engineer so they can trade off like fast-paced development versus high quality of service, right? If you don't change your code, then it's way easier to have good response times. So that's our broadly the goals, right? And what I will do here is I will take you to a journey how you might start out with trying to achieve that goal and do that and talk about the pitfalls and then explain some things you can do better and you can do worse. So, very first thing you might want to do with this API is you want to apply external monitoring to it. External monitoring is the notion that you have an agent sitting somewhere on a different server outside of your infrastructure, and it reaches out to your service every minute or every collection interval and makes a request, and then it measures, is this at all working? Is your site up? And if so, what's the latency? And these are the diagrams you usually see if you are doing that. It's actually good for measuring availability. It's good to alert on outages. This is the very first thing you should do. But it's actually pretty bad for measuring user experience. So, because actually you're not measuring any user, what you're really measuring is just a robot coming to your site. And very often you just hit the front page, you just hit / the root, which is served from cache most of the time. So these durations here usually are just a measure for the network performance between you and the monitoring agent. So it certainly has some problems. But there's actually a far more severe problem than actually, there are a few problems. So let's talk about this one. This is a funny thing. Maybe I can demo this right away. So this is how a request latency graph looks like on a internet is very slow. Yeah, there we go. So this is how the data looks like on a very high granularity. You have these measurements of maybe 15 or 20 milliseconds. If I go to a 2-hour range, then, oh yeah, network is just terrible. Yeah, good that I have screenshots. Great. Yeah, so you still see the full data, but actually if you go back like 4 weeks and more, you won't be able to see the actual data anymore. And many people don't realize this. If you look at the values here, the scaling also adjusts, but this is a 4 here, right? This is not a 20 that we have seen. Here we have the data from the last 2 hours, they're over here. The values are much lower than what we see before. So why is this? It looks crazy. If you go back more, it's even worse. This is a year's scale of data, year's worth of data. So the basic problem is we are displaying here a total of maybe 500 values across the x-axis, and we collected 1,400 data points per day, which is times 300, around 400, 500,000 data points we have for the year. So we are going back from 500,000 to 500 data points. This means every data point we display here, this is an aggregate of 1,000 data points. So you have to make choices. And what's the usual choice? Well, we just take the average. And the actual average data doesn't necessarily have much to do with the original data. So you see what kind of variance you have in there. And that's actually a, yeah, so taking the average is just doing gross injustice to your data here. You're seeing a lot of effects. And actually things, I always complain a little about line graphs. So you note here that we are just using discrete steps and not disconnected lines, as Grafana does, for example, or like many other products do. For this kind of measurements, drawing a continuous line between those two things is completely meaningless. It's just, it was 2 requests who happened to be at a certain time. There's no guarantee that a request which have been like on the 30-second mark here would have a latency somewhere in the middle. So there's really no point here. So the best way to represent this would actually be just dots, saying I had some samples here. If you do that, you can do that actually with a tool. And then you can also draw much more data points. You don't necessarily just have to draw the, let me try if I can do that live. You do not necessarily only have to draw the roll-ups, but you can just show all the data that you have in there. So you will see a lot of sprinkles everywhere around, which is actually just dots for the individual measurements. And actually, with Seconus, we have this funny property that we don't throw away data ever. So we just store the 1-minute data for years. And it means that even like a few days back, it's really hard to see here. But the idea is that you have, for this interval, which is a 20-minute interval, you actually have 20 measurements, and you have 2 modes, and you have some outliers. So this is how your data actually looks like. And you can use this histogram aggregation method, we call it histogram aggregation, to do that. And I did put it here on the slide. So you see the modes again. So here's the lower mode, here's the outliers, then the mean value fluctuates somewhere in between. And if you look at the maximum values over some 1-day intervals, it's up there. So basically, if you are looking at this kind of latency graphs at a scale of weeks, you have absolutely no idea how the actual measurements look like. And this is a pretty serious issue with a lot of graphs you see. And actually, if you throw away your 1-minute data and roll it up and only store the roll-ups, you are completely blind to these kinds of effects. Right, great stuff. So we have so far only talked about a very, very basic way of monitoring, which is just external monitoring, pinging the service from the outside. Log analysis and log files might be the ultimate thing for monitoring. Log files are unbelievably great. Basic idea is every time you make a request, you write a log out with some basic information about that request, including the time of completion, the request latency, basically, usually you take the time of arrival, not the time of completion, how long it took, and you can add further metadata here. You can do the HTTP return code, you can do the full URL that was requested. So it's very, very rich. It's super trivial to add logging instrumentation. Well, it's subtle, but you can start with just printf, which is like way more easy than other things. And the only drawback with logging is that it can be pretty slow, actually because it's so expensive on the data side. So a log line may be 500 characters if it's just verbose JSON, or maybe you can get away with 200. So it's 200 bytes. A single float value is just 4 bytes, or I think 4 bytes. Right, so it's very heavier. And you're not only collecting one every minute, you might have thousands every minute. This might actually work for low-volume APIs very well. APIs are actually everywhere. So what we, for example, do is we collect I/O latency APIs, data on I/O latency APIs for the block devices on every disk that we have in our data center. These are like millions of requests every second that come in, and this is an interesting API. Also, syscalls are a very interesting API to look at. And you might think about just collecting latency information about all syscalls that you make. I know that Sysdig has some pretty nice visualizations and tooling for this. And it's a goal, and actually also possible, I'll talk about this later, to collect it in a monitoring tool. But you cannot, actually, you can physically not collect syscall data with log files, because you will make syscalls for writing the log files for every syscall, so you will have a problem there. But if you can afford to do logs and it's fast enough for you, this is in just a brilliant way, because it conveys the full information that you have about your data or about the API. The main drawback is that it's just super expensive. So what I've put here on the chart is just a way to visualize log data and to actually get out the numerical digest, what I would call it, the numerical digest of the logs. So ideas, this is a timeline view of your API. You get a request coming in, you get the request going out, and it took some defined amount of time. And actually, at which point in time here would the log message be emitted? If your request comes in, request goes out, at the end, right? Important subtlety. You only know how long the request took if the request is finished. You won't see in-flight requests in your log, well, at least if you do the standard stuff. So actually, if I want to do this request latency chart, which I introduce here, you always want to put the latency on the end, because only then you know when the request finished, so you can complete your chart to a certain time team when you are at that time. So and visualizing in this way, you actually have a pretty good way to visualize your API, complete API information, latency information that you have. You have the request completion time on the x-axis, and you have the latency on the y-axis, and this chart gives you just a perfect overview about all numerical data that is in there. And now you can ask some mathematicians what to do with this data. This is basically, if you give them a chart like this, they will be extremely happy because they know what they're dealing with. So if I now have my mathematical hat on, I will just look at this and say, well, great, I have all this latency information. I will just forget when the request arrived and project everything to the y-axis. And then I have a lot of dots here on the y-axis, and then I can maybe do a histogram. So this is a latency histogram here. Or the other thing I can do is just project to the x-axis and say, well, I don't care how long the requests actually took. I just care when they arrived. And this is here the realm of queuing theory, not queuing theory, but stochastic processes, like this might be a Poisson distribution you see here. You have also theory from that angle. And the third angle, which is just maybe an aside here, the request for its whole duration might not actually be doing work most of the time, but it might has been waiting in a queue before it was actually like processed. So you might have some internal states that this requests had in the middle. And if you want to go deep into the theory, what's happening within the request, then queuing theory is the angle you wanna look at. But this, from this perspective, you can see everything. Right. This was the mathematician's view. If you are going to your sales or your marketing team or to your CEO, he might actually have a pretty other view about this thing. Because actually every single request through your whole infrastructure serves the purpose of serving your users. If you are looking at HTTP requests, every single HTTP request will be some user, and they might be happy or less happy. Or they might be the Google bot and don't have emotions, but they still want to be served. So this is a thing that is just important to stress from time to time, that every request has to do with user experience. There are always users waiting at the other end. And if you are just taking averages or checking about, or the percentile was a little bit low, it always means that real users were affected. So you should care about all your requests and don't throw away data about the requests and just take care of every single one. Okay. Now, basically, we have seen what we can do with logs, and we have seen what we can do with external monitoring. With logs, the problem is always sometimes you can just not afford to use logs, because just logs are incredibly voluminous. This is one of the only ways you can really get big data, and just analyzing high volume APIs with just logs is just very slow and very expensive. So sometimes you just can't do logs. You need metrics, right? So what do you do with API metrics? What sensible choices do you have? So one common choice what you can use to monitor your API is to use mean values. Important thing to note is you have to first decide on what your reporting period is, say a minute, and you take all requests that came in that minute, and you look at or completed in that minute actually, and then you take the average of all the latencies that were observed. So average is this nice formula, just the sum divided by the number. It's great, and you can use that for monitoring. Yeah, so this has the great advantage that you are actually measuring your users. This is not completely artificial data. If users are requesting sites which load slowly, then this average will go up. It's very cheap to collect compared to log files, just a single data point per minute. The problems are that you are compressing a lot of information into a single value, and there's the famous quote by Optimizely, Dogan from Optimizely, is measuring the average latency is like measuring the average temperature in a hospital. So don't really care about the average temperature, you care about the temperature of your patient, which is lying in front of you, and the average temperature might not help you so much there. So it can get screwed in both directions. You have the one large value, which could be just hours, completed there will skew the average up a ton. And actually, you might have a lot of requests here being served from cache, which skew the average to the lower end. So both things can happen. You're never really sure which of both happen. And actually, there are more funny effects. So this is an API, and then you see the API. So the mean value of the API latency computed over minutes. It looks fairly okay here. You sometimes see the outliers. So there's one request which took really long, which drags that up. And then you see complete madness here at the sides. Somebody have an idea how that madness might be caused? Yeah, precisely. You've seen that this is just at night, so there's no volume on the API, and then you're dividing by a number which is close to 0, so anything can happen. Yeah, you might not want to alert on the mean value here. It's not good. So, yeah, so you want to do better than that, and of course you all know about this already. You can actually get rid of most of these problems by taking, instead of the mean value, a median value, which median is just take a central value out of here so that the amount of values which are larger and that are lower is equal. So it's a central value. A lesser known method is the so-called truncated means. So the idea is you interpolate between the mean value and the median value by throwing away the extreme values. So you're truncating your data set by, say, you're throwing away a third or half of your requests, and then you just take the mean value here. Combine the advantages of both methods. I've not seen used it a lot. I don't think we offer it like directly in our tool, but it's certainly a thing you should be aware of when you are designing such a system or working with these values. That might be a viable alternative to means or medians. Deviation measures are also interesting to look at if you want to know how much noise is in your data. Standard deviations are generally bad because they suffer from these very same problems with outliers. They can affect the standard deviation very heavily. So a little bit better than that is the mean absolute deviation, where you just sum the absolute deviations and not the squared absolute deviations that you would do for standard deviation. Right. Okay, so next step is actually percentile monitoring. And I know many of you are already doing this. The basic idea here is that instead of just reporting the mean value, you want to get some more insight into the full distribution of your latencies. So a percentile is basically a value which divides your data set in two parts. For example, the 99th percentile, the upper part should be below 1% and the lower part should be below 99%. And there's always a special case when you just hit precisely one sample, then it will not sum up to 10 here, but only to 9. So the definition is actually more subtle than you might think. And percentile is actually non-unique for a related reason. So for example, here the 90th percentile can just be everything from here to here, since the condition is always fulfilled that less than 10% is above and more than 90% is less than 90% is below. So you can go down to here or up to there. It's all 90th percentiles. Might be confusing. You might have thought that the 90th percentile is something unique. Well, actually, you can make that unique and just make a choice. Maybe you just say you always take half. And Wikipedia lists 8 different ways to make percentiles unique. So always ask some question, which percentile are you meaning? So it might actually not be well defined at all. So I mean, if the volume is very high, then usually there's not so much of a question. But if you're just 2 data points, it's actually a good exercise. If you're just 2 data points, what the 33rd percentile of this? Just can be anything in between, or actually should be the lower one. The 50th percentile can be anything, because every cut in the middle divides the data set in half. It doesn't matter which value you choose. And the 33rd percentile is the lower end, just only the lower end. But anyways, this is a fun exercise, but it's also more subtle than most people are aware of this definition of percentile. Right. So what do you have to do percentile monitoring? Well, you actually, again, very important, you select your reporting period first. You say, which request am I looking at? A 1-minute slice. Then you measure the 50th, 90th, 99th, 99.9 percentile, or whatever set of percentiles you choose. And then, for example, you can use it for alerting. So you alert when it goes over the threshold value. Some pros and cons. Pros are you, again, measure requests by actual people, not synthetic requests. It's pretty cheap to collect, store, and analyze. It's robust to outliers, so a single request doesn't affect the percentile much. So negatives are here, upfront choice of percentiles is needed. So you need to know which percentiles you're looking at. And the second point, percentiles cannot be aggregated. And I'll talk about this a little more. So this is how it looks. So this is the 50th, the 90th, and the 99th percentile. So the lowest one directly competes with here. So remember how that looked like. And now the 50th percentile. So 50th percentile, you know the spikes to the top are gone. So you're seeing this robustness here. The 90th percentile is actually a little bit more fuzzy, but it still looks pretty stable. And the 99th percentile is just, you see a lot of outliers going on. So this is like, at this point, it gets a little bit fuzzy. And this is also expected. If you go higher, you will see more noise, because then the outliers will start to affect your percentile actually in that range. Interesting bit here. At night times, when the volume is low, you still see all that problems. So this problem just doesn't go away if you are using percentile monitoring. The percentage of percentiles will be very high if you're just not seeing much requests. Yeah. So then here's the point again. Percentiles can't be aggregated. And this is also a fact which is a little bit underrated or less well known in the community. If you are computing, let's say you have very many levels of aggregation that you can look at. For example, if I have a 1 minute period here and a 1 minute period here right next to it, calculate the 50th percentile here, 50th percentile here. What's the 50th percentile of the overall 2 minute period? The answer is you just have no idea. You just have to recompute it over the 2 minute period. Can be, you have bounds, it cannot be lower than either of the two, lower than the minimum, it cannot be higher than the maximum, but you can construct examples where it's either of those. Same if you have 3 database nodes and you have the 50th percentile over the same 1 minute period of all 3 of them. What's the overall percentage of the whole database cluster, the overall percentile? Answer is you just don't know. You have no way to calculate this, except just collect the raw data, get all latency requests to the central place, and then calculate the percentiles there. It's the only, you cannot do anything else. And so there are like actually three aggregation levels usually see. First of all, the time aggregation, second service level aggregation, and also for the same service, the endpoints, right? You don't have slash, and you have many different endpoints that are served. You might be interested in the whole aggregate of all requests you were serving across all endpoints. So there are at least 3 different aggregations, and for each of those you have to make choices. And actually, fourth choice, you have to choose the percentiles that you want to compute. So if you have a 90th and a 50th percentile, you have no way to compute the 75th percentile from there. So all of this needs to be computed from raw data. So you're making a lot of choices, and it can explode, and it's actually can, if you just want to do it properly and calculate everything right, then this explodes pretty soon, because you have to multiply the amounts of percentiles you collect for every endpoint, for every aggregation level, for every time period, for every percentile, just like thousands of percentiles for a single service. This is a little bit bad. So people actually don't care much. They say, I don't care if it's plus minus 5% if I'm doing the aggregation wrong. And this is actually what I got when I talked about this at Monitorama this year. At one fan of mine, then I don't really know who he's working for, but he applauded me and said, percentiles can't be aggregated. Finally, somebody's making that point. And then John Rouser, he's a data scientist at Snapchat, and said, well, actually, he's pretty annoyed by that statement, because you actually can get pretty meaningful values if you just take averages of percentiles. And well, I said, actually, you make mistakes, and it's actually a serious issue, and you can do better. And I just he twittered that. Actually, it's more like a letter, but it's a tweet. And then he said, well, actually, you can aggregate percentiles, and here's how you can do it. So this is like the gist of a 10-page blog post where he does a simulation with different distributions of request latencies and different percentiles that are calculated. And then he said, well, actually, it's not so bad. If your latency distribution follows this and this, then the average of percentiles is not too far off of the correctly calculated percentiles. This is okay. I was like, okay. Right, he has really thought about this. Well, maybe I should just aufgeben. Well, but I didn't, and I looked at actual data. So actual data is never so nice as is hypothetical data. So this is a heat map representation of all requests that are made in a certain interval. So I will talk about this in a bit. But the important bit is you can actually calculate the true percentiles from this information. So what you see here in red is the average percentile over 1 minute periods. So you calculate the percentile over 1 minute, then you take the average over an hour. So this will get a schätzer, I don't really know what the English word for this is. So estimation for the 90th percentile. 90th percentile, correct. And below here is the true percentile. So this is an error of just 300% that you made just there, which is pretty significant by any means. And actually, first thing all the people ask here is if this always goes in the same direction, and the answer is no. Just it flips like right here, and it's at least 150% error right here in the other direction. So it's pretty crazy, the errors you can see if you just aggregate percentiles on the nose. There might be places where your data is better behaved, but this is not even the worst examples that we had, where you can get away with just averaging percentiles. But most of the time, you just don't know, you don't have any bounds for the error you are making, and it can be pretty far off. So, new chapter here. So far, we have basically seen two different kinds of statistics that we have applied to operations data, and they have two different properties. The first property that you want from a statistic is that it's robust. Right? If you have an outlier, then it doesn't affect the statistic much. For example, percentiles are robust. And the second property you want is mergeability. And this relates to what we have seen here. So you can compute the statistic of the joint data set from the individual data sets. So this is mergeable. And actually this, yeah, okay, I'm using much time here. So I don't go too much into the details. But essentially I'm saying here percentiles can't be aggregated means percentiles are not mergeable. So these are two desirable properties. And I made a little chart of what the properties are of different aggregation measures that we've talked about. So mean value is mergeable. If you have two means of 2 minutes, then you can get the total mean, at least if you have stored the count along with the mean. So you know how many samples you averaged over. With the median, you don't have this mergeability property. You cannot tell what the median was, but it's robust. You gain that. And a standard deviation, it's the same story here. This is mergeable. If you are also tracking the count and the mean, then the standard deviation is mergeable. It's a nice exercise. If you are mathematically interested, try to come up with a formula for the aggregate standard deviation. And the interquartile range, some people will know this, it's you take the 25th and the 75th percentile, take the difference. This is a good measure for the deviation you have in a data set. This is robust but not mergeable. And so are percentiles per se. They are robust, but they're not mergeable. So it really looks like you have to choose between the two. And this is a basic trade-off. Either you can do averages over them and do sensible aggregation, but you will be susceptible to outliers, or you get it the other way around. And now comes the big surprise, histograms. So histograms are, the idea is pretty simple. To collect a latency histogram, you just have to decide on a binning of your Y scale here, or your latency scale. You just you just bin the scale into certain intervals, and then you count how many samples fall in those bins. And you just store for each of those bins the count. And you have to just globally decide on one binning. This is actually, and then we have a good way to do that. And then these counts, you can store them quite efficiently if you use gap encoding for them. So you just don't store a large array of all, I think we have 32,000 different bins, but you just basically store key values. Right, so you're retaining, if you store histograms, you're retaining the full distribution information of your latencies. You're not throwing away much. It depends how much accuracy you lose, depends on how large your bins are. So you can store that. Actually, many people record this already. They use in their monitoring agents, they're accumulating histograms, and they use that to calculate the percentiles, but they're not forwarding the histograms to the monitoring backend. Some people do. Google gave actually the talk after mine at Monitorama, and they were saying, well, we actually just precisely do that. We store for every endpoint the histogram, and then we aggregate, get it later. So you can actually do it, and like big companies do that already. And compared to logs, the amount of memory you need to store it on disk is just minimal. It's like we have an average of 300 bytes per histogram we are taking in. And those can be massive. So we do that for I/O latencies, which have millions of samples in a 1 minute interval, maybe hundreds of millions even. So just to give you an impression how that looks like. So this is actually, so we have this is a year of data. So here we have a total of 35 million samples for each aggregation period of 1 day. And if I hover over that, you see for every day the complete latency distribution, which is very boring here. But you see like how that evolves, and you can also calculate stuff on top of this. So these are some different APIs, and you see how the histograms change over time, and I overlaid the percentile, so you see the 50th percentile here. So usually you would just have this value here, but you can, on top of this, just store the whole distribution. Right. So what do you gain? Why should you care? So first of all, histograms look nice. Okay, good. Maybe not such a big point. So histograms are robust, so you just capture all information. They are not as, like, it doesn't really make sense to say it's robust, but in a certain sense it is. It is not distorted by outliers. It just accepts them and stores them. So it's not, it doesn't, don't lose anything. But the really amazing thing about histograms and the root of their power is that they're mergeable. And they are trivially so. If you have two histograms with the same binning, you just add the counts for each bin. It's trivial. And you can do that across time. You can do that across service levels. You can do that across endpoints. And more than that, you can actually derive all the different, or at least approximate to a good precision, all the statistics we were talking about earlier. So you can, sorry, I don't have that on the chart. You can compute the percentiles and the mean values from the histogram. So then now you can go and first aggregate the histogram and then calculate the percentiles. And this is precisely how I produced these graphs here. So you can get the true values by, actually here you see our query language. We select a bunch of histograms, then we aggregate the histograms here over a window, then we take the percentile, or we take the percentile first, and then we aggregate over a window of time. So you can swap that around, which would be not possible if you just have the numeric stuff. So here's another example how that looks like, and this is our most beautiful example because it's just so nice that you can see so much. So you see you have 3 request modes. So you have one mode that is served very fast, that's here, probably lying in cache. And then you have one thing that spins off here and one thing that spins off here, and you have in the middle another little maximum here. So you see 3 different kinds of users that are using your API. We often see that with like mobile users or users on different carriers which have different network latencies. So you often see like the kind of latency distribution there. Right, and in this case, it's actually very funny because you actually see how that distribution here changes over time. And this was actually a bug in which caused in a web server, which was appending to a list every time you made a request, and this list retrieval got slower and slower. So one of the modes was getting higher and higher. You could just really see also the performance behavior of that in the histogram. Right, and this is just the same data, and then I overlay the mean values and percentiles and rates. You can also calculate the rates. Right. And okay, so far I've just talked about that histograms are a great way to do monitoring, which gives you the possibility to aggregate your data properly, to do correct computations, to gain more insight. But actually, it goes further than that. This is a very simple exercise if you have the histogram data. Say your acceptance threshold of your users is something like 40 milliseconds. This is hypothetical, but at some point, people will get really annoyed. They will say, well, this took longer than a second to load. This is unacceptable for me, or longer than 10 seconds. If you have the histogram data, you can just count how many people had that bad experience. And if you compare this, many of the problems we had before are just going away. Because yes, you were serving 99% of your users badly at night, but it was only 2 users. So I'm not getting paid for that. And also, if you want to have sensible reporting, you can just sum them up. So you do integral across this day, and then you know at the end there were a total of 4,000 requests or 4,000 users that were not getting the right performance out of your API. So this kind of analysis are very easy and very simple to do if you have the right data set to do it on. So just expanding on that idea, I've not gotten around doing this, but sometimes you can also estimate the amount of financial loss you're suffering because you know what your rate of users is that will go to a different service depending on how much latency were. So if it takes longer than 3 seconds, they have a certain probability to go away. If it's longer than 15 seconds, then they have another probability, and one could try to build a little bit more sophisticated models on top of that. So I don't know how well this would work, but there are you can think of a lot of things that you can apply and you can do with that data. But I mean, just very simple reporting is possible and pretty trivial. Right. So I will close with this. Some takeaways here on the last slide. Don't trust your line graphs, at least on scale, because you have spike erosion. Don't aggregate percentiles, really, if you must do, but if you can get away with storing histograms or using logs for doing your reporting, that's much better. Keep your data. If you're throwing away the 1-minute data, just have the averages, then not much information left. And strive for meaningful metrics. And have a peek at INDB. Don't forget it. Thanks.